This presentation is on the element distinctness problem. This is for COT 5405, Design and Analysis of Algorithms. Our presentation plan is to briefly introduce the element distinctness problem. We'll give a small example of a decision tree model. And finally, we will prove the lower bound for the element distinctness problem. The problem statement. Element distinctness is when you give me a sequence of numbers, let's say an integer array or a number array. We'll call that sequence A. And I will give you back yes or no. You give me an array, I'll give you back true or false, yes or no. I'll give you yes if every single element in A is distinct. There are no duplicates. I will give you no if any of the elements are repeated. If AI is equal to AJ for some I and J where I does not equal J. They are repeated elements. I will give you no. All the elements are distinct. I'll give you yes. Here are two examples. If you give me the first array, I'll give you back true. There's no repetition of any elements there. They're all distinct. The second array is an example of no or false. We can see that 3, 5, 6, all of these elements are repeated somewhere in the second array. So next we will describe the decision tree model of computation. This decision tree model is a way to model computation in such a way that the program, the steps that we need to exact in order to find a solution is a labeled tree. In this tree, a node that is not a leaf has a label. This label will compare two indices in the array. We'll pick index I and index j, for example. The edges in this tree, we will use a relational operator, such as less than or equal to or greater than. And finally, the leaf nodes of this tree will be the output. In this case, it will be some kind of permutation of that input array. The execution of this program will begin at the root, and we will go down the tree. At each node, we will compare index I to index j. Or at each node I and j, we'll compare element I to element j in that array. Okay, so here's a small example of the decision tree model. We have, you give me the array 3, 10, and 4. And we'll look at first index 1 against index 2. So this is a 1 indexed array. We don't have index 0. So we compare 3 to 10. We go to the left because 3 is less than or equal to 10. We compare index 2 to index 3, and we go to the right because 10 is greater than 4. And finally, we compare index 3 to index 1, index 1 to index 3, and we go to the left because 3 is less than 4, less than or equal to 4. So that we arrive at the permutation 1, 3, 2. We have the smallest element first, the largest element, and then the middle element, which is what is reflected in our example array. And the path we need to get to this leaf is left, right, then left. So starting from the root, left, right, left. Left, right, left. So we saw that each leaf is a permutation of that initial array, of that input array. So we can say that using this decision tree model for sorting, this tree must have at least n factorial leaves because for any set of n elements, there's n factorial ways to permute those elements. And so the height of this decision tree is the log of n factorial, otherwise omega n log n. So this is the lower bound of sorting. So next we will look at the lower bound for element distinctness. In element distinctness, we get only two answers, yes or no. And there must be n factorial leaves, all giving yes answers. We need to prove this. This is what the remainder of our presentation will be about. And one powerful intuition will be the utilization of n-dimensional geometry. Geometry will be a very fundamental part of our argument. So finally, we will prove the lower bound for the element distinctness problem. So our claim is that the time complexity is omega n log n. For this problem, this is the lower bound. This is the best we can do for element distinctness. So before we start, we're going to interpret this array as some kind of n-dimensional vector in order for it to work with our geometry intuition. The values in this vector will be just restricted between 0 and 1 inclusive. We might break this in some examples. And we're going to let this notation RL, region of L, be the instances where leaf L is reached upon the execution of this decision tree model. So this will be the region of L. And this will also tie into our geometry intuition, our geometric intuition. So here we see an example of, here we let n equal 2, so this is a two-dimensional vector space. So we have three regions here. On the left, there's a triangular region that surrounds the green dot. In the middle, there is a line that runs through a red dot. And on the left bottom, there's a triangular region that surrounds a green dot. So the regions that surround the green dots, any vector that's in here, and remember a vector is just a permutation. So let's say we have 0, 0, 4. Let's say 0, 4 falls in this region. This region will work. Element distinctness problem, our algorithm will return true. Oh, the two elements are distinct, because 0 does not equal the other element. In this case, the length of it's 2 dimensions, so the length of our initial array is 2. We can also see that we have the similar case for this bottom region. Let's say we have 4, 0. 4 does not equal 0, so it will return true. And we see that the region that this line that intersects this red dot, any vector that falls along this line will give us false for the element distinctness problem. 0, 0, 1, 1, 2, 2, 5, 5, 3.6, 3.6. All of these vectors that lie along this line will return false for the element distinctness problem. So here we're casting this type of computation geometrically, and we'll expand this to more dimensions. So so here's going to be here is our roadmap for this proof. We will first show that the region of L is connected. So any region that leads to this leaf L, that's a yes leaf, is connected. Our second claim is, given a vector X that contains distinct elements and a vector Y that is a different permutation of X, it must be the case that X and Y both reach different distinct yes leaves. And finally, the number of leaves has to be at least n factorial. The number of yes leaves has to be at least n factorial. So these are our three claims that we will show in this proof. So I'll describe the idea of convexity soon, but convexity implies connectedness. So we will prove this first claim, going back, that R of L is connected, the region of L is connected, by a quick sketch, and then we will show a picture on the next slide. So this sketch of the proof is we have a vector space S over the real numbers. We will take a subset C of this vector space S, and we'll show that it's convex for all X and Y in C. So a line segment connecting X and Y is also included in C for all of X and Y. So C is convex. So now we consider the affine combination y minus t x plus ty, and we know that it belongs in C for all x and y and all t of the interval 0 to 1 inclusive. So this is an affine transformation, or affine combination. This implies that convexity is invariant under affine transformations, which we'll show on the next slide. And this further implies that a convex set in a real topological vector space is path connected, and furthermore, it's connected. Convexity implies connectedness. Convex implies connected. And so we'll see an example of a convex space on the next slide. We'll look at a convex cube. It's a little more complicated than our previous two-dimensional space, but it's still simple enough to visualize. 3 dimensions is still simple enough to visualize. And a reminder of the definition of convex is for all points x and y in our cube, there exists a line that goes through x and y. Let's imagine the entire cube for a moment. You can pick any 2 points inside of a cube, and we can find a line that goes through x and y and stays inside of our cube. This line does not leave the cube. If we pick a point here and a point here, we can find a line that connects the two. If we pick this corner and this corner, we can draw a diagonal to connect the 2 points. And just to orient ourselves with this cube, here are the axes. x1 goes left to right. x2 vertically up and down. x3 kind of goes in and out of the page, if we can imagine that. And when we make a comparison in our decision tree model, so let's take, for example, so we're at the root and we're considering this entire cube, and in order to leave the root, we need to make a comparison. We'll make a decision. So here we'll see what happens if x3 is greater than x1. Let's say we're going along that path in our decision tree model. So we start with the cube, and then if we follow that path, x3 is greater than x1, we will end up, so let's say this is a wall here that cuts our square into 2 wedges. It cuts it into 2 slices of cake. This back half, the part away from us in the cube, that back half is what happens if we follow our computational model, our decision tree model, along the edge where x3 is greater than x1. We'll end up back here. So we start with the cube that's convex, and after we follow this edge in the tree, we arrive at this wedge shape. And the insight here is that this wedge shape is still convex. And what we show in the previous slide is if it's still convex, we also know that it's still connected. So this region that we've arrived at is still a connected region. And so we can further interpret this for more comparisons further along the tree. We'll keep dividing this tree into, this cube into more and more wedges, more and more slices, and each smaller slice that it turns into will still be convex. Next, we will show the claim that given vector x contains distinct elements, and then a non-trivial permutation y, both x and y will reach different yes leaves. So you may be asking, what if x and y reach the same leaf? Well, that's a great question. Let's assume for the sake of contradiction that x and y reach the same yes leaf. We'll call that leaf L. So we showed from our previous claim that the region of L, R of L, is connected. Therefore, every path P from x to y we know is entirely inside of L. It's entirely inside this region of L. It's inside this leaf, and it's inside that whole region in that leaf. And we will show that there's some kind of permutation Z in P in this path that leads to a no leaf. That will be the crux of our proof. So as I said, it's a proof by contradiction. We'll define a continuous function. It's like a difference function. So function f of w, where we take one element and another element, and we take the difference. So let's say f of x is less than 0, f of y is greater than 0. And this is a continuous function. So if you remember from calculus, the mean value theorem says that there exists some value z such that f of z is equal to 0. We start at a negative value, f of x is less than 0. We end up at a positive value, f of y is greater than 0. Because this is a continuous function, it at some point has to cross that line, y equals 0, or f of z is equal to 0. So we get that f of z is equal to 0, and as we defined f of z, that's when we take an element zi, subtract it from zj, and that's equal to 0. And that implies that there's some element zi that is equal to some element zj inside of this array z, which means these two elements are not distinct. This leads to a no leaf given this array. This is a contradiction. And in order to, for the sake of completeness, we will show a small lemma for this proof. We need to show that there exists an I and j such that xi is less than xj while yi is greater than yj. So we'll illustrate this with a small example. We have an array x with the elements 10, 3, 99, 2. We have y as defined. It's a non-trivial permutation of x, 9, 2, 3, 10. We'll define function s, which basically sorts x. What it does is it sorts x. So we apply this permutation to x, so it becomes 2, 3, 10, and 99. We plug x into s, and it just gives sorted order. That's what that function does, is it sorts x. And we see applying the decision tree, we get 3, 2, 4, 1. So the first element is the third largest element, the second element is the second smallest element, the third element is the largest element, the last element is the smallest. So we will apply this ordering, so we'll apply this ordering to y, and we see how it changes the order. So these elements will become first, so 2 goes first, and then 10 follows along with it. This goes second, so since 3 is the next element, 2 will be next. Since 10 is the third element, we know 99 will be next. And 99 is the last element, so 3 will be last. And we know that x and y are distinct. And that's how we're defining this problem. So when we sort x, there will be an I-j pair, such that when I is smaller than j, while our sy of I is greater than sy of j. In other words, at some point, y cannot also be sorted. When we sort x, and then we apply that permutation to y, it cannot also be sorted. Which means there is some pair, like yi, yj, that is not in increasing order. So we've shown that lemma. And we will conclude our proof by showing the number of yes leaves is at least n factorial. So how many yes leaves can we have? Given n elements, there are n factorial ways to permute them. There are n factorial different ways to order those elements. Therefore, we have shown that the number of yes leaves is at least n factorial. And to conclude, for this element distinctness problem, the tree must have at least n factorial leaves, and the height of the tree is log of n factorial, which is big omega n log n, and that is our lower bound for the element distinctness problem. Thank you.